Hi, my name is Emmanuel Godin and welcome to this introduction to SDL-RT. Let's first have a quick look at the origins of the language. In the late 80s, the telecommunication world was booming with X25, the GSM and Internet. There was a strong need for a notation to define all these new protocols. For that matter, the International Telecommunication Union, the ITU, defined a graphical notation to describe the dynamic of a protocol and some abstract data types to describe the information that was exchanged. But the most important thing about SDL is that there is an execution semantic within the standard so that there is no misunderstanding or misinterpretation of the model. This is a major feature of the modeling language. It makes sure two implementations of the same protocol by two equipment manufacturers are compatible with each other. Once the standardization body has published a new protocol, the telecommunication manufacturers have to implement it. For that matter, for efficiency reasons, developers were writing C code at the time. But they really liked the graphical representation of the behavior that was used in the protocol standards. So they started to mix the original SDL graphical representation with C code. That is what initially led to the definition of SDL-RT. Since then, the SDL recommendation has evolved, and now the SDL standard accepts C-type declaration and manipulation directly within the graphics. Since its basic principle, SDL-RT has been further extended and finally combines a consistent number of standard notations and concepts. SDL for its ability to describe functional architecture and detailed behavior, MSC to express requirements in the form of an expected behavior or to trace execution of a model or of a real target, real-time operating system services, and in particular the semaphore concept to synchronize tasks executing in parallel, as well as the notion of a priority on the task over another, UML for its graphical representation of classes and for its deployment diagram, C and C++ for the data types, the atomic instruction, its performance, and its capability to connect to other software modules. Full documentation is available for free on sdlrt.org. It has been written to be legible as opposed to the original SDL recommendation, and its textual format is XML based. Now, since SDL and SDL-RT have been used for decades, there has been quite a number of evaluations of the benefits of using such notations. The first benefit is quite obvious. Because of their graphical representations, the models show a clear view of the architecture and the interfaces of the different parts of the system, making the model self-documented. As a consequence, the organization is clearer. The roles of the different parts of the system are well defined. Since the tools supporting SDL or SDL-RT have simulation capabilities, a lot of the bugs that are usually found very late in the development process are discovered early. As a result, the number of errors have been evaluated to be divided by a factor of 5, which is quite substantial. Finally, as a consequence of the two previous benefits, the overall development time is reduced by around 30%. We could summarize these benefits with the following. Thanks to its graphical but detailed abstraction, SDL-RT helps to handle complexity, ensure maintainability, and ease communication between the stakeholders. Frankly, that's quite a lot of benefits. Now, in which domain, on what kind of application can I use this notation? Well, obviously, because of its origin, it can be used on any telecommunication system, and more generally speaking, on any communicating system. That is quite a wide range of systems considering equipment tend to all communicate with each other. For example, the IoT, network protocols, or the Industry 4.0. But because of the benefits we just listed, it also reached out to other domains where the level of quality is paramount, such as avionics, space, military, automotive, medical, and so on. To evaluate if SDL-RT is suitable for a specific problem, it is important to understand what it is, but also what it is not. We will see in more details that SDL-RT is based on finite state machines exchanging messages. More generally speaking, it is an asynchronous language. In that world, the sequence of events is more important than the absolute time when the event occurred. That is opposed to a synchronous language, which is based on a clock, where, for example, the sensor value is read on a regular basis, and the delay between two samples is paramount. That is particularly true when there is a library of mathematical functions that rely on the regularity of the samples. Also, I know it may sound obvious, but this SDL-RT is not related to the simple direct media layer development library used to develop video games. Okay, now let's dig into the details of an SDL-RT system. First of all, the architecture of the system can be graphically described with SDL-RT. The system is composed of agents. An agent can be a functional block that can be further decomposed in subblocks and so on until we reach the process level, which is actually a description of a behavior with state machines. All the processes, that means all the state machines, run concurrently in parallel. The architecture also describes the information that is exchanged among the different agents. The agents are connected by channels. Messages with possible complex parameters follow the channels. Once a message is sent from an agent, the sending agent continues its execution. That is a key characteristic of an asynchronous language. A few words about the blocks. A block is a high-level function entity. It is used to organize and architecture the system. The block architecture should not change through the development process. Blocks are usually not implemented as an execution entity. Processes are the lowest level of the architecture. A process is an execution entity. Processes execute concurrently even within the same block. Each process has an implicit message queue. The process reads the queue when it is done handling the previous message. So message-based communication does not interrupt the current execution. Therefore, it is asynchronous. A message is a piece of information which is sent from an agent to another agent. A message is defined by its name. It can have 0 or many parameters. Parameter types are any C or C++ types. Messages can be grouped in lists. Messages can be defined at any level of the architecture. Here are a few examples. My first message is a parameterless message. My second message has 2 parameters. The first one is of type character and the second one is of type pointer on an int. Also, my message list is a list of my first message and my second message. Since processes are executing concurrently, some synchronization might be required to handle concurrent access to a shared resource. This is inspired from the semaphore resource available from any real-time operating system. A semaphore is a common resource that can be defined in any agent and that can be accessed by any process. Here is how to declare a semaphore. Binary, mutex, and counting semaphores can be declared here, with some options such as priority inversion or an initial state. Now that we have discussed the architecture and the interfaces, here comes the core of the notation, the behavior and data which are in the process diagram. The process behavior is a graphical state machine in which the variables are declared and manipulated in C or C++. Let's start with the data. The types can be defined in the agent declaration box, or they can be declared in an external header file and included in any agent. The same applies for a variable declaration. It can be done directly in the agent or in an external file. The variables declared in a process are local to the process. They cannot be directly accessed by another process. The variables declared in a block are automatically visible in the whole underlying architecture of the block. Regarding the communication, each process has an implicit message queue. The message queue is a FIFO, first in, first out policy. When the state machine gets to a new state, that means it reads the message queue. The oldest message in the list is read and removed from the queue, and the corresponding transition is executed until the state machine gets to a new state. When a message is sent, it is put in the receiver message queue, and the sender resumes its execution. Processes usually do not send messages to themselves unless it is the only way left to go. A very important point: a timer going off is actually a message in the queue. That means the timer going off does not interrupt the execution of the process. It only creates a new message. It is put at the end of the list of pending messages in the queue. Now, let's look at the behavior of the process. It is a finite state machine. At execution time, when the process starts, it will first spontaneously execute what we call the initial transition or the start transition. There can be any type of action in that transition: message outputs, task creations, timer starts, and so on. At the end of the transition, the state machine ends in a new state. Once in this new state, the process reads its message queue. If there is nothing in the message queue, it hangs on the queue. When a message arrives in the queue, it is evaluated. It is considered as a valid input in that state. In this example, if we are in state 1, input 1 and input 2 are expected. If we receive input 3, then the message is discarded. The key aspect of the state machine is that the same input might not produce the same effect depending on the state it is in. In this example, if the input 2 is received while in state 1, the variable myVar will be set to 2, but if it is received while in state 2, the variable myVar will be set to 0. Please note, a transition can be triggered by a message, but it can also be triggered by a continuous signal, and we will detail this in a few minutes. Because it is graphical notation, a transition might end up with a lot of symbols. So it's possible to describe the same state with the same symbol used several times at different places. For example, the state 1 input 1 transition is described separately from the state 1 input 2 transition. This is equivalent to describing input 2 and input 1 in state 1. At the end of the transition, the process will go to a new state. It can use the same graphical symbol as the starting state, even though it is clearer to separate the new state symbol from the old state 1. As we already mentioned a few minutes ago, apart from messages, another possible trigger is a continuous signal. A continuous signal is actually not a signal. It is an expression that is evaluated before looking at the message queue. There can be several continuous signals, and in that case, they have priorities. In this example, when the process gets into state 1 with A equal 15, and input 2 in the queue, the resulting behavior will first evaluate the continuous signal with priority 1 is a greater than 10. And because it is true, it will trigger action 2. At the end of the transition, the state machine stays in state 1, so the second continuous signal expression is also evaluated, and because it is also true, it will execute action 1, which also ends up in state 1. Finally, we get a chance to handle input 2 message, which was waiting in the queue, and execute action 3. Messages received while unexpected in a state are discarded. This is considered to be a normal behavior. To avoid that, an unexpected message can be saved to be treated when the state machine reaches a new state. At that point, the first saved message will be treated before the other messages in the message queue. In this example, message 1 is saved in state 1 but triggers a transition in state 2. Let's say message 1, message 2, and message 3 are received in that order while in state 1. First, message 1 is handled and it is saved. Then message 2 triggers a transition that ends in state 2. Once in state 2, the saved message 1 triggers a transition that ends in state 1. And finally, message 3 triggers a transition in state 1. Another way to deal with unexpected messages is to use a star in the input symbol. That means all other messages that are not explicitly listed in the possible inputs will trigger this transition. It is a sort of a default input. The star can also be used in the state symbol, so the combination of a star state and a star input means that whatever message in whatever state that do not explicitly trigger something will trigger this default transition. Once the transition is triggered, let's have a look at the possible actions in the transition. It is possible to send a message, start a timer, cancel a timer, take a semaphore, give a semaphore, create a task, that is another instance of a SDL-RT process, to execute any C or C++ code, to evaluate an expression with graphical cases represented as branches, to call a procedure, create an object, an instance of a class that is defined in another diagram, or to connect to another branch of code that helps to improve the graphical layout of the state machine. But it is also a way to factorize the behavior. There is also a transition option, which is equivalent to an if-def in C. For the declarations, the graphical symbols are not connected to anything. They are sort of floating in the diagram. There is a symbol to declare a procedure. A procedure is actually a state machine that can be called anywhere within the main state machine in order to factorize behavior. There is a symbol to declare the variables that are manipulated in the process. The variables are only visible in the current state machine. They cannot be accessed from the outside. That is why some people compare the variables in the process to the attributes of a class and the transitions to the operations of a class. We will see that this is actually quite correct. Let's see the details of the message output. The message output symbol contains at least the name of the message to be sent. The receiver of the message can be identified through its name or its ID. In case the message goes out of the SDL-RT system, a C macro name can be specified to detail what is to be done when the message is actually sent. If the message should follow a specific path, it is possible to specify the name of the gate or the name of the channel the message should go through. The parameters of the message, if any, are copied to the receiving process. That is why the receiver should have the corresponding variables declared to receive the value of the parameters. The PIDs of the process can be retrieved with the following keywords. Offspring is the PID of the latest process that has been dynamically created by the current process. Self is the PID of the current process. Parent is the PID of the process that created the current process. Sender is the PID of the sender of the last message received. Let's now move to timers. First, there is no need to declare a timer. Just start it. The timer is identified by its name, and the time unit is the system tick. When the timer goes off, it becomes a message in the queue like any other message. The name of the message is the name of the timer. Messages already present in the queue will be treated first. The timer does not have any priority. When a timer is cancelled, if the corresponding message is already in the queue, it will be removed from the queue. The timer message can only be received by the process that started it. The timer goes off only once. There is no concept of repeat timer. The timer can only be started once. If restarted, the previous one is cancelled. That is ideal for checking a response has been received within a given amount of time. Now, semaphores. The concepts are the same as the one found in a real-time operating system. So binary, counting, and mutex are available if the underlying real-time operating system supports them. And the way they behave are real-time operating system specific. From the model point of view, SDL-RT semaphores are identified by their names and they are automatically created at startup. Just as a reminder, by default, taking a semaphore is a blocking action if the semaphore is not available. The execution will resume when the semaphore is freed. The semaphore declaration will specify some options such as the starting semaphore state or if it will create a priority inversion. In order to avoid being blocked too long, a timeout can also be provided. Its value can be expressed in ticks or with the keywords forever or no wait. The return value indicates if the take attempt was successful or not. If OK, the take was successful. If error, it was unsuccessful. So, we have been through the different concepts in the language that relates to real-time operating system services such as messages, timers, dynamic process creation, semaphores. Now, let's have a look at how the object orientation is handled. A class is the descriptor for a set of objects with similar structure, behavior, and relationship. A class symbol is a basic rectangle. In order to represent the attributes and operation, the class rectangle can integrate sub-rectangles. Now, in real-time system, it is important to distinguish active and passive classes. An instance of an active class owns a thread of control and may initiate control activity, like a thread or a process or a set of processes. On the other hand, an instance of a passive class holds data but does not initiate control. That means passive objects are called within the context of execution of an active class. For that reason, in SDL-RT, there are additional graphical representations for active classes. The main difference is the thick line to represent the box. There is a representation for a system, a block, a class of block, a process, and a class of process. All these are active classes. Since an instance of an active class has its own thread of execution, there is no direct access to its attributes from another object that does not have the same context of execution. The only way to interact with the active object is to exchange messages. For that reason, active classes do not have any attributes listed, and the operations are actually incoming and outgoing messages going through gates. A gate defines an interface that will be connected to the surrounding architecture when the class is instantiated. In this example, process class pphone can receive messages call and hang up through gate genv and send out messages connection request, connection confirmation, disconnection request, disconnection confirmation through gate G-switch. One of the key characteristics of a class is the possibility to specialize it. Specialization defines is a kind of relationship between two classes. The most general class is called the superclass, and the specialized class is called the subclass. That means the subclass inherits from the attributes and the operations of the superclass. But the subclass can add or redefine the attributes or the operations. That is specialization. Two classes can be associated. It is basically a relationship between the two classes. An association has a name, a role, and a cardinality. It should be understood this way. Class A knows of cardinality instances of class B as class B role name. In this example, an instance of company will know 5 instances of person known as employee. Two other relationships are part of the SDL-RT recommendation: aggregation and composition. Aggregation and composition define is a part of relationship between two classes. In an aggregation, the contained and the container classes can exist independently. In a composition, the contained classes cannot exist without the container. A package is a container for classes. It is simply referenced by its name. In order to refer to the classes in the package, the use clause must be used at system level in the SDL-RT model. Once the use package is stated, any reference to a class implicitly refers to that class in the package. It is also possible to specify the package name before the class name in the class symbol. Referring to another package in the use clause will point to totally different classes with the same name. Now that we have looked at the basic relations between classes, one of the key representations in SDL-RT is the ability to show the relation between the active and the passive classes in the same diagram. In this example, the class of process P central is composed of one instance of user factory named myUsers. myUsers handles 1 to any number of users. On the left, P central admin is a specialization of P central. That implicitly means that an instance of P central admin will have a myUsers attribute that handles a set of users. In other words, myUsers are visible in the context of execution of one of the instance of P central admin. Please note that when it comes to the underlying code, the passive classes are generated as C++ classes and the active classes are generated as C or C++ state machines running as an independent thread of the operating system. The SDL-RT architecture is abstract. It does not say anything about the computers or the processors on which the agent will be running on. That is the point of the deployment diagram, to describe the physical deployment of the system on real machines. There are very few symbols in the deployment, so let's go through them and explain what they represent. First, the node. It is presented this way with a name and an attribute. A node is a physical processing resource, a computer or a processor, for example. Second, the component. A component is a distributable piece of implementation. It can either be an executable or a file. A connection is a physical link between two nodes or two executable components. It is defined by its name and stereotype. There can also be dependencies between the elements. Dependency between elements can be represented graphically. A dependency from a node to an executable component means the executable is running on the node. A dependency from a component to a file component means the component needs the file to be built. A dependency from a node to a file means that all the executable components running on the node need the file to be built. Node and component attributes are used to identify a potential receiver. In this example, CPTB can connect to CPTA via mynet connection by using node.a.mynet.id attribute and cpta.mynet.id attribute. Now, let's go back to object orientation in SDL-RT. We have seen how classes could relate to one another, but let's see how they apply to real-time concepts. In particular, we will look at how inheritance and specialization apply to state machines. One of the very interesting aspects of object orientation with SDL-RT is that it applies to the behavior itself and that it is quite unique among other modeling technologies. Let's illustrate this with a class of process called mySuperClass in a package called myPackage. It defines transition input 1 in state 1. It also defines a gate with the possible incoming messages. In our case, the gate is called myGate and the possible input is input 1. Now let's define another class of process called myClass that inherits from mySuperClass. MyClass will define the transition input 2 in state 1. It also adds input 2 to myGate. Since it inherits from mySuperClass, that means an instance of myClass will have both transitions in state 1, input 1 and input 2. The gate will also define the two possible inputs, input 1 and input 2. A subclass can add a transition to a state, but it can also refine or redefine a transition. The subclass can simply re-specify what is done for a given input in a given state. A special task symbol with a triangle is a way to call the superclass transition. Any action can be added before or after the superclass transition, and finally the superclass ending state can also be called. So the subclass can partially or completely ignore the superclass transition. In this example, the subclass myClass inherits from mySuperClass. In state 1, when input 1 is received, myClass first calls for the transition of the superclass, then executes action 2, then goes to the next state of the superclass. The classes and their relationships are defined in the class diagram, and the class diagram is in a container called a package. So first, a system has to specify which package to use. Then, the dynamic class defined in the package can be instantiated in the architecture. In this example, process A is an instance of myClass that is defined in myPackage. Then the gates are connected to the surrounding channels. That means the messages defined in the channel must match the messages defined in the gate. A complementary view to what we have been discussing so far is the MSC. The SDL-RT message sequence chart, MSC, is similar to a sequence diagram. It is a dynamic view of the synchronization and the exchange of information in the system. Time flows from top to bottom. The vertical lines represent a structural element such as a task, the environment, or an object, a semaphore. Arrows with an open arrowhead are asynchronous. They represent message exchanges or timers. Arrows with a filled arrowhead are synchronous. They represent semaphore manipulations or operation calls. An MSC can be used as an expected behavior, a specification. It can also be used as an execution trace. Let's have a quick tour of some examples coming from the recommendation to illustrate the MSC. In this example, there is a caller process and a server process. The server process is in the idle state. The caller sends a connection request message, starts a timer in case there is no reply, and goes to the idle state. Then the connection confirmation message is received from the server. The caller then cancels the timer and goes to the connected state. In this example, the execution of both processes is concurrent. Messages are sent and received asynchronously. Here we have the keyboard process on the left and the my phone book object on the right. The keyboard process calls the set URL operation on the myphonebook object. While the operation is processed, the process is considered suspended and the object has the control of execution. Once done, control is returned to the keyboard process. In this example, the execution of both instances is synchronized. The object is executed in the flow of execution of process, and process is on hold while the object is executed. Last example, with a semaphore protecting a shared resource. myproc1 creates and takes the semaphore mysem to access the shared resource. The attempt succeeds, so the semaphore is not available anymore. Process myproc2 tries to take the semaphore, but because it is not available, it hangs on its request. Until process myproc1 releases the semaphore. Then, immediately, the process myproc2 can resume execution. It is possible to write loops and alternatives in MSCs, but still, an MSC is basically one scenario. Now, the overall system scenario is not one and unique. It is actually a combination of scenarios. That's what the HMSC, the high-level MSC, is for. To put together in sequence or in parallel a bunch of simple scenarios. In this example, the system starts and is in the disconnected global state. Then the system goes to either a failed connection attempt scenario or a successful connection attempt scenario. These are references to detailed MSCs. In this case, it is one scenario or the other. Let's say it succeeded. The supervising and the data transfer scenario are next and executing in parallel until the system disconnects. Okay, we saw a lot of graphical representation. Now, how is all this stored? Well, SDL-RT comes with an XML schema that is quite legible. Here in this example, the symbol has the ID SIM12. It is of type SDL task. It contains the text phone ID and so on. It is based on the default colors. Its position is 488, 511 and so on. So it is easy to read or parse the SDL-RT XML if needed. To summarize, SDL-RT offers a wide range of graphical representations. Library of components in the class diagram, object-oriented specification, also in the class diagram, system architecture in the block diagram, interface definitions, also in the block diagram, application deployment in the deployment diagram, real-time concepts with the behavior diagram, key points in the design, also in the behavior diagram, and dynamic scenarios in the MSCs. To conclude, SDL-RT is C and C++ code graphically organized in a set of representations of the architecture, the communication, and the state machines. It is precise, even though it relies on some specifics of the underlying real-time operating system semantic. And it is definitely aiming at code generation on target. Among the available products we have, the SDL-RT based one is Pragmadev Developer, which is part of Pragmadev Studio, which is free in the case of a small system. There are a few examples provided with the tool you can play with. Integration on Win32 or POSIX allows you to generate code and animate the model on your host. Give it a try!